Welcome to this video lecture on the subject transmission lines and antennas. So in this lecture we are going to discuss about skywave propagation. So skywave propagation refers to phenomenon where radio waves are transmitted from Earth's surface into the ionosphere and then reflected or refracted back to the Earth. So this allows radio signals to travel beyond the line of sight and cover the longer distances even around the curvature of the Earth. So it is important for medium to long range communication. So amateur radio, shortwave broadcasting and long distance military communications. So basic concept of skywave propagation. So it occurs when radio waves, especially in high frequency band 3 to 30 MHz, are transmitted upward into the ionosphere. So ionosphere is a layer of Earth atmosphere that is ionized by the solar radiation, and this ionized layer can reflect or refract the radio waves back toward the Earth's surface, allowing for long range communication. So the transmission mechanism, a transmitter sends out the radio wave, initially travels upward in a straight line. Once the wave reaches the ionosphere, it encounters different layers of ionized particles. So depending on the frequency and the state of the ionosphere, the wave is either reflected or refracted back towards the Earth's surface. So the radio wave then travels across the Earth's surface and is received by a receiver located at a distance. So the ionosphere is made up of several layers of ionized particles that reflect the radio waves. The key layers are D layer, that is 60 to 90 km above the Earth's surface. So this D layer absorbs the low frequency radio waves during the daytime, causing them to be attenuated or absorbed. It has a strong effect on the propagation of lower high frequency signals. And next is the E layer, 90 to 120 km above the Earth's surface. So this layer reflects the radio waves in the lower high frequency band 2 to 5 MHz. During the day, it plays a significant role in reflecting the signals over medium range distances. It is weaker at night but still influences the signals. Next, F1 and F2 layers, 120 to 500 km above the Earth's surface. So these are the most important layers for skywave propagation. The F1 layer is the weaker during the day, while F2 layer becomes more important at night. So the F2 layer reflects the high frequency signals above 10 MHz, which allows them to travel long distances. The strength of the ionosphere and its ability to reflect the radio waves is influenced by the time of the day, solar activity and season. So how skywave propagation works? So several factors influence the transmission and reception of radio waves. First is the reflection and refraction. So reflection occurs when radio waves hit the ionosphere at a critical angle and bounce back towards the Earth's surface. So the refraction occurs when radio waves pass through the ionosphere, bending according to the ionosphere electron density. The angle at which the radio waves hit the ionosphere, called incident angle, determines whether it will be reflected or refracted and the distance it can travel before returning to the Earth. So next is the skip distance. When the radio waves is reflected back to the Earth after refracted by the ionosphere, there is a specific range at which the wave is likely to return. This distance is known as the skip distance. It depends on frequency, angle of incident, ionization level. So the low frequency signals below 10 MHz have longer skip distances and travel over great distances, especially at night when the ionosphere is more ionized. High frequency signals above 10 MHz may have shorter skip distances, but they can support multiple hop bounces to reach very long distances. Next is the critical frequency. The critical frequency is the highest frequency that can be reflected by the ionosphere back to the Earth. If the frequency of the radio wave exceeds the critical frequency, the wave will pass through the ionosphere and continue into space. The critical frequency depends on the electron density, which changes with the time of the day, solar activity, and geographic location. So next is the skip zone and multi-half propagation. So skip zone is the region where radio signals cannot be received because the waves are reflected away from the earth. It occurs between the transmitter and the first reflection point in the skywave propagation. So beyond the skip zone, the signal can be received due to the reflection. And multi-hop propagation, here the signal can undergo multiple reflections, hopping from one ionospheric layer to another. So next, these are the factors affecting the skywave propagation. So first one is the time of the day. Here during the daytime the ionosphere is more ionized due to solar radiation, which enhances the ability to reflect the radio waves. However, high frequency signal may be absorbed by the ionosphere, and low frequency signal are more susceptible to absorption by the D layer. So at the night, the ionization decreases, especially in the E and F1 layers, allowing for longer range communication. So the F2 layer becomes the dominant reflective layer at the night, allowing higher frequencies to propagate further. Next is the frequency of the signal. So lower frequencies are typically used for long range communication. They can reflect off the ionosphere more effectively. And high frequencies may work better during the day, but they are more susceptible to attenuation or skipping during the night time. Next is the atmospheric condition. Factors like weather and geographical location influence the ionospheric condition, which affect the skywave propagation. These are the applications of skywave propagation: shortwave radio broadcasting, military communications, and maritime and aeronautical communication, emergency communication systems. These are the assessment questions. Thank you for listening this lecture.